So it's really a pleasure to be here, an honor. And the title of my talk today is Pricing and Product Design in a Data-Driven Economy. And so let me go and explain the title a little. I've been interested in pricing for a long time. Started with work on dynamic pricing. And then I got interested in product design ideas from several angles. One of them was risk management. So try to design real options around products to mitigate risk. And finally, more recently, looking at discrete choice models. But when you go into industry and start getting data sets, and people are expecting that you would do something with those data sets, then you can become very frustrated because you may try all of the techniques under the sun, statistical techniques, machine learning techniques, and say to try to fit a demand model, and yet it may be that, you know, as hard as you try, you're not getting something that could really be used as a pricing engine. Something that could, you know, really help in terms of pricing guidance. And then you feel frustrated because all of your theory, you're ready with all of these ideas. You just need the data to behave. And sometimes the data refuses to behave. And so sometimes you're challenged, you know, to what to do in cases like that. And so the first topic I'm going to cover today is product similarity, a key to design and pricing of products. That's work with HP, and to some extent it's a response to a situation like the one I just described, where it was really not possible to fit a demand model that could lead to a good pricing engine. And the second topic I'll be covering is work with Sabre in the design and pricing of bundles and ancillary products. And the last two topics are a bit more academic in nature, but they all are related to the topic of pricing and product design, and they all, at one point, require handling large data sets. So let me start with this product similarity. If you look at products, they usually had a set of attributes, and for each attribute, you have a set of levels, and there are a large number of potential products. You know, presumably, you can have combinations which each attribute is each level, and so you have a very, very large number of potential products, but the number of products that you see in the market is usually a small fraction of the potential. Products can be represented by vectors in attribute space, and the standard idea is to use prices, attributes, and sales to fit a demand model, and then use it for price optimization. And what happens if all efforts to do this fail to provide good pricing recommendations? So what are you going to do? Are you just going to say, well, I tried and I failed, I'm going to walk away? Well, that's not good. Huh? So what else can you do? It's not trivial, but there are things you can do. In fact, you can get a fair amount of traction even when you fail at this task. So let me tell you a little bit about hedonic models that are used to value attributes. So a hedonic model uses sales data to fit a function of this form. Price is a function of the attributes plus some noise. Now the US government has been using hedonic models like this for a long time, and they use them to measure inflation, because as time goes on, products evolve, and so it's very difficult to compare a car from 2013 to a car from 5 years or 10 years ago, because they have different features. And so by actually valuing the features, they can come up with a better estimate of the true change in price. But we plan here to use hedonic models for our own purposes that have nothing to do with measuring inflation. So let me tell you a little bit about what you could do with hedonic models. First, you need to select a functional form, and there are many you can select. Here are just two. And then even after you select a model, you need to somehow fit it, and this is part art and part science, because there's so many choices under the sun. You could use elastic net, which is a sort of constrained regression that puts penalties on the norm on some of these vectors beta. You could use something like fused lasso, and in this case, when you have a series of attributes that are presumably increasing in quality, you want them to be monotone in price too, so you may want to bound the difference. You could find that there's massive multicollinearity and decide to work on the principal components, so you want to come up with a sparse principal component analysis. And then you can cluster and then fit. So there are many, many possibilities. And you need to work through many of them to really find out what works. There's no given recipe that would tell you what would work at any given point. It really depends on the data set. So what can you do once you fit a model like this, a hedonic model? You can approximate the expected price of another product, either existing or not. And you do this by just using Taylor's expansion, first order Taylor's expansion. And essentially it tells you that the price of product X tilde, the expected price is the expected price of product X plus this quantity here, the gradient times the difference in the components. And so once you have that, well, what can you do? You can create a neighborhood of products that are somehow similar in the sense that are not too different, in terms of their imputed prices, and they're not too different in terms of their attributes. So even the choice here of this distance metric is something that needs to be carefully chosen. And once you do this, then you can create a heat map by plotting the difference in imputed prices to the difference in actual prices. And you can overlay information such as sales or the age of the product to create a heat map. And a heat map would look something like this. Okay? That's a heat map. So there are different brands, so the different colors represent different brands. So these are products for different brands. And in the horizontal axis, you see the difference between the imputed price and the core product that you selected, the product X. And on the vertical axis, you see the relative change in price. And so you can immediately see, once you visualize the heat map, how you could potentially use it. You could potentially use it to, for example, understand that there's an area here where you don't really have any good green products. Okay? And there may be an area here where you may be overcrowded with green products. And there may be products like this one right here that perhaps are old products that are candidates for discontinuance. So there are many things you can do once you have your heat map. The first could be, for example, try to explain what's off the diagonal and see if there are interaction defects that you may want to include. And then once you include the interaction defects, then you have an improved hedonic model, and then you can go back and forth. You can, once you're confident you have a good hedonic model, you can identify products that are overpriced or underpriced relative to the imputed values. You can identify regions where brand presence is high, identify products for discontinuance, identify regions where brand presence is low, and also identify product configurations with high potential profit or value. So the way to do this is you try to come up with a configuration that maximizes the spread between the value of the attributes and the cost. If you identify one such product, then those such products could either have large surpluses if you price them low, or large profits if you price them high. So these are products that are potential win-win for you and for your customers. And so we built at HP a product similarity tool based on these ideas that have feature evaluation, market analysis, feature adjusted prices. It's used for SKU discontinuance and for new product introduction. Where possible, we fit demand models and come up with price recommendations. But even where demand models do not fit, the tool is still quite useful. And so this was done with a large group of people. The tool has at least 15 man-years already invested into the development of the tool. It was just released. It's being used worldwide now with over 100 users. These are the names of the people. The principal person there is Jose Beltran. And some of my students here at Columbia spent internships and really helped with the data analysis. I'm very grateful to them. So that's the first topic. And as you can see, we went in with some preconceived notions, and we walked away with a very different way of thinking about the problem. So the second topic is the idea of design and pricing of bundles and ancillary products. This is actually some work done with Sabre, with Richard Ratliff at Sabre. And let me walk you through the idea of bundles. Bundling is the practice of selling 2 or more products in a package. And it's a strategy based on different customer segments having different valuations for combinations of products and services. And it's practiced among many different industries. In bundles, if you develop them right, provide you sort of something near to mass customization. If you go back to Dell's idea of building a computer to your specs, that really didn't work that well because it was complicated for individuals to configure all of the details and complicated for Dell to actually manufacture all of these different computers with different configurations. And what it rapidly evolved to was to product families that you could customize a little. Okay? And those usually provide good value to customers and simplified the decision on the part of the customers, and also simplify the logistics on the part of Dell. And so it's a strategy that, if it's executed well, provides economies of scale that reduce cost and complexity while providing near mass customization. So the question is how to design and price bundles to maximize profits while providing the product variety that people want. So the design and pricing of bundles is intrinsically linked to the question of estimating customer valuations. And this is linked to behavioral economics, to bounded rationality, and the integration of psychology and economics. So I'm showing you all of this because in the design and pricing of bundles, you cannot completely ignore the psychology of how people make decisions. And so even to the point where the people who suggest that people are not only rational but predictably so, and in that case then you need to try to exploit that predictability. And here's a little example that comes from Ariely in a famous experiment where they were comparing an electronic versus a bundle of electronic and paper subscription to The Economist. And they figured they could bias the decision towards the bundle just by offering the paper-only subscription at the same price as a bundle, because then people perceive the bundle as a bargain. Okay. So we've tried to do our analysis, and then at the end, perhaps tweak it a little to take into account bounded rationality. So let me go and talk to you now about bundling and unbundling in the airline industry. The airlines unbundled luggage handling in 2009. As you know, many of you are paying. How many of you paid for luggage handling coming in? Only a small fraction of you. Okay. So it tells you that if you're flying domestic for a short period of time, then a lot of people prefer not to have that bundled. And so that unbundling had a significant impact because profits rose by $2.3 million that year after a loss of $3.3 billion the previous year. And airlines collected $2.7 billion in baggage fees. So you can see that without those baggage fees, it's unlikely they would have made a profit. So airlines are now striving to go away from the classical, traditional fares with restrictions that are very opaque to designing bundles of products that could either include transportation as part of the package, and these are known also as branded fares, or, and an example of this would be Air Canada. Air Canada has these Tango, Flex, and Latitude that provide more amenities and flexibility in increasing prices. But also bundles that consist only of ancillary products, like Delta has these $199 bundle that covers the first bag, priority boarding, preferred seating, discount in economy comfort, and enhanced mileage. So how do you design these things? The problem is to determine which attributes to include in each bundle and to price the bundles to maximize profits. So when you have a combinatorial number of bundles that you can design and an infinite number of prices, the problem really seems very complicated. Bundles also need to be constrained so that customers cannot reconstruct them at a lower price by purchasing more primitive bundles. So they need to be arbitrage-free. And so we have a little theorem that when customers have linear utilities, then bundles are arbitrage-free if and only if there exists a positive vector of attribute prices. This is actually straight from finance, just applied to the idea of bundling. And this helps because it reduces the problem to designing the bundles and just pricing the attributes, and the bundled prices are just simply the sum of the attribute prices. So that theorem really helps in the design and pricing of bundles. So let me give you a simple example that would give you an idea of the potential improves in revenues when you use bundles as opposed to a la carte prices. So this is a very simple example with 4 market segments and 3 attributes. So market segment 1 has market size of 100, and they have valuation 5, 12, and 45 for attributes 1, 2, and 3. Now suppose we were trying to price attribute 1. We're going to sell attribute 1 a la carte. Attribute 1 costs us $3. So obviously we don't want to sell it at 0 or at 3 because we won't make any money. So the real options is either 4 or 5. If I price it at 5, I make $2 on 100 customers. That's $200. If I price it at 4, okay, I make $1 on 220 customers. So 4 is optimal. Okay, we all agree 4 is optimal there. And likewise, if you go to attribute 2, you would find that 10 is optimal, and for attribute 3, 4 is optimal. So you have that, if you were pricing a la carte, the optimal a la carte prices would be 4, 10, and 40. And this is what customers would buy. Segment 1 would buy the 3 attributes. Segment 2 would buy attributes 1 and 3. Segment 3 would buy attribute 2 only. And finally, segment 4 would buy attributes 2 and 3. And you would make $4,360. And that's optimal that you can do by selling a la carte. But what if you sell bundles? Okay, if you sell bundles, you can get an increase in profits by 22.5%. And the way you do it is you sacrifice market segment 3, and you sell these bundles at those prices. This is this vector, internally consistent vector of attribute prices that came from that theorem that I discussed a few minutes ago. But the very interesting thing here is that these internally consistent prices are not meant to be there for people to buy a la carte, because they're very suboptimal if you were to offer the attributes a la carte at those prices. If you were to do that, your profits would drop from $5,000 to $2,200. So you have to really be careful on how you design and price the attributes, okay? And you have to be careful not to announce your vector of attribute prices and give the customers the ability to buy a la carte at those prices. So the problem is to maximize the expected profit subject to a bunch of constraints. You want incentive compatibility, individual rationality. This efficiency constraint is a no arbitrage constraint, and perhaps other business constraints. So these are hard strategic problems that need to be solved infrequently. An airline is not solving this problem every day. So we developed bounds and heuristics that produce bundles and prices that significantly improve profits over ad hoc designs that have fairly small gaps between the value and the upper bound. Okay, I'm not going to show that to you, but I'm just going to show you the tool that Sabre has developed. And they're now offering this to several airlines. Okay, so this is my third topic now. Hope I'm doing okay on time. And this is a little bit more academic, but very interesting to me and potentially very applicable. And this is the issue of constraint assortment planning. You can imagine that you have a set of products. Each product brings a certain revenue or reward. You can think of it as a profit contribution. I'm just going to use revenue for short. And for each product, there's a certain probability of selling the product depending on what assortment you offer. So presumably, the larger the assortment is, the more product J is competing with a larger set of alternatives, and usually that probability would go down. And so there is some cannibalization going on among the products, and so the question is which subset you should select. That's the unconstrained assortment problem. But often, you have constraints. And there are a class of constraints that can be modeled as totally unimodular constraints. A large class of interesting constraints that fall into that pattern. And I'm going to show you some of those constraints. So you can have a bound on the maximum number of products. So a customer comes to a landing page and you want to offer them an assortment of products. There is a certain number that you can offer there. Or it could be that you have 3 categories of products and there is a bound on the number of products that you can offer in each one of these categories. And so, in addition to these two that I have just described, there are these other three very interesting constraints that fall into this category of totally unimodular. One is this idea of optimal location and assortment. The idea there is that not only do you want to select the assortment, but where you're going to place it. So imagine you're in a supermarket. It's not the same if you put a product at eye level, okay, or at the end of the aisle, that if you put it at shoe level or knee level. Then the other one is when you're doing both discrete pricing and assortment. So in this case, not only are you worried about the assortment, but you're worried about what price you're going to offer. And you can have a finite price menu. In a special case of the finite price menu, it's when it consists of only three prices. Okay, infinity, meaning that you're not offering the product, so the product is removed, the regular price, and perhaps a promotion price. So then this decides which products are going to be offered, which not, and among the chosen products which are going to be promoted and which not. Then there's another one that comes up frequently when you have products of different quality, and this is to ensure that the prices are quality consistent. Over the last few years, I've seen a number of examples of quote-unquote optimized prices in airline settings where business class is priced lower than coach. And the reason for that is that the dual variable of the capacity constraint for the standard product is larger, and so you have excess demand for the standard product and excess capacity for the premium product can lead to these inconsistencies in quality pricing. And so you can handle that too via a total unimodular constraint. So here's the example of the location. You're worried not only about the product, but also about the location. And now I'm going to talk a little about how to solve this for a variety of choice models. The plain vanilla model is the basic attraction. And the form of the basic attraction model is that you have n items. You have n items, and each one has a attraction value. And given an assortment X, the probability that product I is selected is of this form. So X is just an indicator of value for the assortment. And this model is quite old. It was developed by Luce in 1959, and then shown to be the result of a random utility model where the randomness comes from an extreme value distribution known as the Gumbel. And so in addition to this model, we've developed an extension that takes to some extent care of a situation where you may be facing severe competition. And this is what I call the general attraction model. You see, in the basic attraction model, in addition to the very well-known problem of the independence of irrelevant alternatives, there's another problem that is quite serious, that if you go back to the basic attraction model here, if I go to a wine store and I want a particular wine and they don't have it, then according to the basic attraction model, then I should either not purchase or purchase one of the wines in the store. Okay? So that's my universe. That's my only alternatives. But if there's a wine store a mile or two away, then I have an alternative. So the amount of recapture, okay, the amount of recapture of demand when my favorite wine store does not have the Vignard Danza that I like, goes down relative to the availability of that wine in other stores, in other liquor stores nearby. So to handle that, we developed this model that we call the general attraction model, where in addition to the attraction value for each product, there is a shadow attraction value. That's between 0 and VI. And then the formula essentially is the same, except that it changes the no purchase alternatives by adding these terms. So by adding the shadow attractiveness of the products that the firm is not offering. Now, if you see that case VI tilde equals to 0 reduces to the MNL, in the case where VI tilde is equal to VI, reduces to the independent demand model. So this model captures everything between the independent demand model and the MNL, the basic attraction model. And these models can be justified two ways. You can modify Luce's axioms, and then you get this. Or you can see it as a limit of a nested logic model when the correlations of the idiosyncratic value of a product, of the same product among different stores, goes to 1. Okay? So if you're not really drawing a new independent gumball, but drawing a correlated gumball for a product among the offerings in different stores, then you get that each store ends up with a generalized attraction model exactly as the one I'm describing here. So what we can do with this is that we can solve these problems via linear programs. So the original problems are really fractional programs with binary constraints, which look hard. And the theorem is that these problems can be transformed into this linear program right here, as long as the constraints are totally unimodular. And these LP formulation that I've provided you for the basic attraction model also works for these more general attraction model that I just described with the shadow alternatives. In addition to this, so first let me say this LP formulation, this joint work with Davis and Topologlu at Cornell. And some of these results extend to the nested logic model, also work with Zim. But we're still concerned that even the generalized attraction model or the nested logic model may not always be able to really capture what's going on in terms of consumer choices. So recently, we've developed a markup chain approximation to random utility models. This is where two of my colleagues at Columbia, Jose Blanchet and Vinit Goyal. And what this model does is you take any choice model, say that comes from random utility, and we can show that you can approximate it very well by a markup chain model that has the following characteristics. You need as input the first choice demands. It's the probability that the customer wants product I in the first place when you pretending that you're offering everything, in a substitution probability, the probability that a customer will substitute to product J if product I is not available. And surprisingly, once you have a model like this, the problem of assortment optimization can be solved very, very quickly and very efficiently via successive approximations. And this is particularly important because there are many instances in where you fit a model and you work very hard at fitting the model, but then the problem of doing the assortment optimization doesn't be hard. So here, you fit a model, you approximated the markup chain, and then you can solve it efficiently via the following successive approximation algorithm. So you think that customers are going to be transitioning between products depending on whether you offer them or not. So initially, you offer everything, and so the reward is RI. But as you iterate, use the successive approximation techniques, you're taking the maximum of the revenue of either offering product I or allowing the customer to transition to a product J and then rewarding them with Gj of t. And we can show that this is a monotone increasing function that converges to Gi, and that works really, really quickly. And then the optimal assortment set under the approximation is just the set of items I such that Gi is equal to Ri. Okay, so that's my third topic on constraint assortment problems. I figured that by now I would be running out of time, and I had the idea of talking a little about the next topic of consumption and fulfillment options. And this is a topic that I've been working on over the last, I would say, 8 years or so. But I have only one slide on this because most of that work is already published and you can easily find it. So the idea of using consumption and fulfillment options comes from the idea of mitigating the risk that either the consumer or the capacity provider faces when demand is uncertain. And so the idea is to use real options to mitigate risk and to reduce the imbalance between demand and supply. And it's useful when capacity is limited and customers are heterogeneous in their flexibility and their willingness to pay. And these real options have applications both in the context of revenue management and the context of supply chain management. And some of the papers that we've written about this are the following. There's one was about partially refundable fares with Oscar Zahin. And in that one, we look at partially refundable fares as opposed to the more traditional situation where, say, an airline would offer either fully refundable or non-refundable fares. We show that the use of partially refundable fares is socially optimal and that they can be designed to really be win-win by improving the customer surplus and improving the revenues for the capacity providers. Then we have a paper with Steve Koo and Robert Phillips about callable services or callable products. The idea there is that you may want to embed an option, okay, so that you can buy back a product. Like an application to this, for example, could be the following. Currently, there's a very large market, secondary market for tickets for events. And if you try to buy a ticket for a hot Broadway show or for a popular baseball or basketball game, you find that it's nearly impossible to buy it directly from the provider. You have to buy it in the secondary market and pay a huge premium for that. And what's happening is that these group of people who are controlling the secondary market are very aggressive at buying up the capacity very early on. So and the capacity providers are very reluctant to get into that game because they have a ticket with a certain posted price. They feel bad of selling you the ticket for $300 when the face value says $100. And so I think they've been very passive about the way they handle this. One way they could, recover some of that market is by making these products callable. Okay? Yes, I'm selling you this product for $100, but I have the right to buy it back for $150, say. Then there's the idea of flexible services. The idea there is that you may have several customer classes. A class, for example, that is price sensitive and very flexible. Another class that has very unpredictable demands, is not price sensitive, and generally, say, would book late. In that case, you could sell like a morning flight from Minneapolis to San Francisco and then delay the assignment of that particular flight, morning flight, until you have enough information so that you can better serve customers that are booking late. So in all of these cases, I mean, I'm just giving you the overall description, but for all of these cases are models and results that actually show that you can do significantly better just by adding a little bit of flexibility. And finally, there is one paper on upgrades and upsells. Upgrades typically occur in situations like I described earlier, where there is often, by design, excess capacity for premium products and excess demand relative to capacity for standard products, so that at the end of the day, to be able to serve your customers who demand the standard product, you would need to upgrade some of them. And it's to a certain extent by design, because often it's not that more expensive, say, to buy a full-size car rather than a compact car, and that full-size car can serve two markets, so it gives you some flexibility. So the question there is, how should you manage the upgrades, and how can you try to not only just give them for free, but somehow creatively be able to obtain something for that premium product that you are giving to the customers. Okay, so all of these fit within the title of product design, because these are features, options that modify the product visually so that you can maximize revenues, mitigate risk. Okay? And with this, I'm going to conclude my talk. Thank you very much.